Yeah, this talk won't be so long as Fabian's talk, but it will still be very interesting. And what this talk is about is the experience that I've collected over more than 1 year now, helping users to use Flink in production or try it out. So everything that happens on the mailing list, is somehow there in this talk. Because I've seen over the time that the questions are actually pretty similar that the users are asking us. And I think there is a lack maybe of presentation and understanding how the basic stuff in Flink works. So the original title of the talk was Troubleshooting Your Flink Application, but I've changed it to Hands-On. So frequently asked questions and answers, what tooling we provide to help you, and also an outlook into the future, how we want to make the situation better. I've thought of this quote when I made the slides. So 1 week of trials and error can save you up to half an hour of reading documentation. No. But I didn't know who the author is, so I thought maybe, I put somebody who certainly doesn't read documentation. I also thought about Dalai Lama. So the first step when you want to start to use Flink is that you write and test your application locally. To do that, you start ideally with an empty project generated by Maven. So Flink is using Maven. You can also use SBT or other tools. But Maven is the thing that we are using and that we understand. So if you have questions to Maven, we can help you. And we provide these Maven archetypes, which generate you a document or a file hierarchy that is properly set up in a Maven fashion. You can also change this Flink Quick Start Java to Scala, and then it will generate you a Scala project. And you can also set the version whatever you want for stable or unstable release. So for starting to develop something in Flink, you don't need to download any archive from the Flink website. You just need to generate this Maven project and import it into your IDE. And it will automatically download everything it needs. Then when you open your IDE, everything starts from this execution environment, which allows you to create your initial data sets and start transforming your data. And the cool thing is that by this execution environment, you locally start everything that Flink would also start in a cluster. So we'll start the same services, and we run the same code that we would run on the cluster as well. So ideally, you can figure out a lot of your bugs already locally in one JVM. Also, something that many companies like is that we provide utilities for unit testing. So you can also specify the expected result of your job, and Flink will automatically start the entire engine for you and test your code. Since we are starting the entire Flink system in one JVM, you can debug locally. So in this case, it's the tokenizer of the Wordcount example. And I've put a breakpoint here to this out.collect. That's when the mapper is emitting the results of this tokenization, which is splitting the input string. And you can see here this string value is, for example, this line here. And then you can see that we have 10 tokens splitted from that input string and so on. So it's super easy to locally step through your functions, see what they are doing, what input they are getting, and so on. So with these utilities already, you should be able to develop a working job locally. And the next step then is to put that job onto a cluster. But maybe you got no cluster. Then there are different options. And I've listed them from easy to harder. So the easiest option is using Google Compute Engine. There is this BD util, I think it's Big Data util, and it ships with the Flink extension. So you don't need to download anything from us, it's shipped by Google. And this will deploy a Google Compute cluster, multiple machines connected to each other with Flink pre-installed there. The second option are cloud providers that give you a cluster that contains Hadoop Yarn. So Flink can run on top of Yarn, And most cloud providers that offer big data solutions also have a pre-installed yarn setup. For example, Amazon has this Elastic MapReduce offering, and for running Flink there, you just spin up your Elastic MapReduce cluster, and then you need to execute these 4 commands: downloading the Flink archive, unzipping it, going to the directory, and starting a yarn session. So that's a matter of 5 minutes. It's very easy to do. And of course, there's the hard way of installing Flink yourself on all machines. So you can also start 10 machines in the cloud and install everything there. But maybe you got no money. And then you can listen to my talk and become a rich big data consultant. And in the meantime, you start a cluster locally. So you just unzip, you just download the file, unzip it, and then use this start cluster command, which will locally start one master node and one worker node locally on one machine. So now we can assume you have a cluster. And there are different ways of submitting a job to it. So the easiest way is to use this bin Flink client, which we also call the CLI front end. So that one allows you to specify the jar file, the name of the main of the class where the code is located. It also allows you to get information out of the job, stuff like that. The second option is this remote execution environment. With that, you can, for example, trigger jobs from inside a JVM. So, for example, when you're working in a company and you want your users to start Flink jobs out of application server, for example, when they click on a button, then you can, from this application server, trigger a job using that remote execution environment. For those that don't like command line stuff, they can also use the web front end. So there you can just click, upload a jar file, and submit it to the cluster. This web front end has the added benefit that it also allows you to see how the operators are looking, so how the job is looking, and also what optimizations the Flink optimizer is doing on your job. Another option of submitting jobs is submitting them directly to Yarn. So you don't necessarily need to start a Flink cluster inside Yarn first. You can also submit the job directly to Yarn. For example, when you have a mixed setup where you run Hadoop jobs and Flink jobs next to each other. And there's a new way which is not yet merged, but very... Huh? In the morning. It will be merged. So tomorrow morning you can also use the Scala shell to submit jobs to your cluster. Yeah, this list might be boring, but I don't know, many people don't know, for example, this remote execution environment. Oh yeah, I thought I have some screenshot for the web, this web job client. So there you can see, here is the job that I've uploaded. Here is a preview of the job. Here you can also see the optimizer choices. So there you can see the different strategies that Flink has come up for executing your job efficiently. So that's a very neat utility when you understand the internals of database systems. Then we also have a web front end for the job manager, which shows you like how many machines are connected, how many processing slots are available, how many jobs are executed, cancelled, failed. You can also see the timeline of a job, so you can see when operators were started, how long they were running. And this is also helpful sometimes to understand the performance implications of different changes in your code. And we have some resource monitoring utilities for your task manager. So there you can also see like spikes in the resource utilization. You can see how active the garbage collectors are. So we have a detailed list of how active the different garbage collectors are in the system. But that's only the theory, and in practice stuff doesn't work. So then you need to debug stuff on the cluster, which is harder. And the easiest way to debug stuff on the cluster is good old system out debugging. You can either use our logging framework. For that you first need to get a logger, and then you can start logging stuff. We log at the info level by default. So everything that is above info, for example 1, will also be logged. But if you prefer quick and dirty, you can also do system out print line. That is still the easy part. The harder part is getting the logs on the cluster. If you're in a non-yarn case, the logs are located in the log directory on each worker node. So each task manager writes to the log directory, which is locally there. So you need to SSH into that machine to have a look at the log files. You can, if you want, mount a shared file system to each machine so that they log into that shared directory. Then you have access to all the log files on all the machines. But then you need to be careful with contention on that shared directory. When all the machines are logging a lot of stuff at the same time, then the system will be basically blocked by this one file system. In Yarn, you can retrieve the logs when you have this log aggregation enabled. Then you are able, for finished Yarn applications, to just do yarn logs minus application ID, and then it will show you all the logs of the task managers and job manager. Yeah, so getting logs on a running application is also doable. For that, you have to select the machine. Then you go to the list of running containers, and there you can click on logs and then get the log file while the application is running. So it looks complicated, but it's not so hard if you've done it a few times. Yeah, and it allows you to have a look at the stuff as it is written by the system. And the log files themselves are also very helpful, actually, if you look to them closely. For example, you can see here the commit that you're using. So many, in particular advanced users, are using snapshot versions, so versions that are not yet officially released. And then it's very helpful for us, also for you, to understand what version you're using, what commits are already in your code. And you can see what JVM you're using or what JVM your system started. So sometimes, I don't know, your administrator has done some nasty tricks to start another JVM than you assume, and then stuff is different than you think. Also, you get a lot of information how the system is initialized, how the different services are configured, and how they're going to behave. Another useful feature of Flink are accumulators. So when you're coming from the Hadoop world, there it's called counters, and they help you to get an understanding of your data. So often when you run your application or debug your application, write your application locally, you have a small test data set, maybe even handwritten, then it's usually perfect. But in reality, data is almost never perfect. There are like special cases, empty fields, stuff like that. And then these accumulators are very useful for counting how many elements are coming in, how many elements are matching a certain filter, and so on. So to use these accumulators, you have to use a rich flat map function. I hate Macs, by the way, because these blue boxes are actually aligned correctly on Windows. I don't know. So when you use rich functions, then you can access this runtime context, which gives you access to counters. So in this case, for the word count tokenizer, each time the flat map is called, we get this element count and add along to it. So this way, you can count how many elements are coming into this mapper function of your word count, which is really useful when your output doesn't look the way you expect it to look. There are different ways to retrieve the results of the accumulator. So they are returned by environment.execute. There's also a new method called get last execution result for print, for example, when you cannot immediately access the job execution result. And inside this execution result, you can get, for example, the long counter, which is this element count. Then the bin Flink blind is also showing you accumulator results in the end. And the job manager is also showing you the result of the long counter or any other accumulator. So accumulators can be anything that can be represented as a local variable on the task manager and then merged on the job manager. So a quick excursion to rich functions, which are really useful for a lot of stuff. So by default, when you implement something on the Java or Scala API, or at least on the Java API, these default functions are single abstract methods. So they have only one method and they are interfaces for supporting Java 8 lambdas. But there's also a rich variant for them. And these rich variants have different methods. For example, the open method where you can pass a custom configuration, and the close method, for example, when your mapper is creating a connection to an outside system that you want to cleanly close. And you get access to the runtime context. And the runtime context allows you to get, for example, the ID of the task you're running on. So imagine you have 10 mappers. Then this get number of parallel subtasks will tell you, okay, there are 10 mappers. And you can get the information that you are mapper number 2. Then you can access the execution config, which contains information that you specify at the local client before submitting a job. Also, I've added a feature to the execution config where you can pass custom serializable objects there. So you can also globally distribute configuration values to all your user-defined functions. For example, all the input parameters that you get from the CLI or that you pass from the command line. Then you get the accumulators and also a feature that we borrowed from Hadoop, the distributed cache. All right, so these features might be sufficient to debug your stuff, but maybe you need a hammer, and that's attaching a debugger, a remote debugger to Flink in a cluster. And both IntelliJ and Eclipse have very nice utilities to do that. So there's a menu where you can start a remote debugging session, and then it will show you the command that you need to pass to the JVM. And here is this suspend equals no, which means that the JVM will just start running. But you can also pass suspend yes, then the JVM will wait until you are connected to the machine. But this waiting only works when you have one task manager, one worker, because otherwise all the workers will be waiting until you're connected, but you can only connect to one worker at a time. So usually I would recommend to not suspend your JVM. And then you need to tell Flink to put this agentlib string that you're getting from your IDE to all the JVMs which Flink is starting. And then you create a SSH tunnel to that machine where the task manager is running. And then you can start, you tell your IDE, please start a remote debugging session. And also you see here that I've put the correct class path here. And then you can really look into the Flink code as it's executing on a remote cluster. I would recommend to make the breakpoints not stop all the threads, but only your own thread, because otherwise the system will kill your task manager because it's not reacting fast enough. All right, so with this, I hope that your stuff is finally working on the cluster. And what you want to do now is tune it. So we bring it to West Coast Customs and get a fancy car. So there are different tuning options. There's the CPU, there's memory, and then there's I/O, but only disk I/O in this talk. And the first thing that you need to do is tell Flink how many CPUs you have in your system. So there's a configuration value called taskmanager.number of task slots. And a task slot is basically a holder for a parallel instance of your job. So when you have 8 CPU cores, I would recommend to give each worker node 8 of these slots for processing a job. But I have a bit more material explaining these slots because it is hard to understand in the beginning what it actually means in practice. So imagine you have 3 machines, each runs a task manager, and you configure each task manager to have 3 slots. So an imaginary system with 3 CPU cores. So in total you have 9 processing slots. You can also tell the yarn session to create 3 machines with 3 slots. So then you also end up with 9 slots. And then when you submit a job, by default, we'll use this configuration value, parallelism.default, which is set to 1. So by default, for example, Wordcount will be run in run slot. So one machine will use one of its executor task threads to execute your word count. Now you can also set a higher parallelism. So you can, for example, say, I want to run 2 instances of that job. And for saying that to Flink, you can either increase the default parallelism. I would recommend to set the default parallelism to the total number of slots you are having, because this way you get the best performance. You can also specify the parallelism to the Flink client. And you can set the parallelism when programming your Flink job in the Java or Scala API. And yeah, this is just for completeness the same job with the full parallelism. But then you can do more. You can also specify the parallelism for individual operators. So in this example, I instruct this write a CSV, which is this data sync, to have a parallelism of 1 only. So we will only we will execute all the operators with 9 instances, but this data sync should only be executed in 1 instance. And it's important to note that all the data will be sent from all the slots on the different machines to this one sync. So all your results will end up on one machine. In this case, only the local results of each machine will be written to the local disk or into the result file on HDFS. All right, so that's for the CPU. This way you can give Flink the full processing power of your cluster. The next tuning option is memory. So you need to tell Flink how to use the available physical memory on each worker node. And I hope you paid attention to Fabian's talk, because it's really interesting. So yeah, we have 3 regions in Flink. We have the basic memory that contains, for example, the network buffers, but also internal data structures. Then we have the managed memory, which usually uses the most part of the memory. And we have the remaining heap, which is free for your own stuff. So for example, when you train a machine learning model, this might live here. Or when you create, for whatever reason, a list of all the stuff that comes into your user-defined function. So inside a mapper, you create a copy of all that stuff and maintain it in a list. And this list will live in this remaining heap space. And there are, of course, configuration parameters for controlling the behavior of the system. So the size of this entire box is controlled by the taskmanager.heap.mb configuration value. In the yarn case, you can just specify -tm, so minus task manager, and then the size in megabytes. And this is the heap size that we'll tell the JVM to start with. Then the system will allocate the network buffers. I'll explain for what they are used later on. And yeah, you can basically change the number of network buffers. And once these network buffers are allocated, I think by default they eat up 64 megabytes. We'll look how much memory is still available in the JVM and allocate 70% of that for the managed memory. So by default, we use a relative amount, this memory fraction, to start the managed memory service. But you can also specify an absolute size if you want. Some typical errors that occur is the fancy out-of-memory exception, out-of-memory error when you run out of heap space, or when your system spends too much time on garbage collection and says, I'm giving up, it doesn't make any sense anymore. Then memory is missing in this blue area. So usually it's not Flink's fault, except you are in corner cases where you have a really small JVM. But other than that, usually this happens because the user code is doing too heavy stuff in the heap. For example, keeping a local list. Then you need to reduce the amount of managed memory. And for that, I would recommend to reduce the memory fraction, for example, to 50% instead of 70%. Then another popular exception is this error that you are not having enough buffers for safely executing a job. So when a task manager receives a job, it calculates whether it has enough resources for safely processing the job. If not, it will just throw an exception. And memory is missing here then in this case. So we have managed memory, these network buffers, and the regular Java objects. And to increase these network buffers, you just set there a higher number. But I can tell you a bit more in detail how to set that number. Because these buffers are needed for transferring data between the operators. So imagine you have a simple map-reduce job on a cluster with 4 processing slots on 2 task managers. So you have 4 slots in total. Then each of these mappers, which are running in parallel on the machines, have 1 output buffer for each reducer. So this is needed for sending the data there. So I've started to draw all the lines which represent logical connections between the mappers and reducers, but I've gave up at some point because it's too crazy. And this is not the number of, or this is not the amount of network connections. This is only logical connections for the system. So actually the system has only 1 network connection between each machine. But still we internally need buffers to transfer the data from the mapper to each reducer. And also the reducers need buffers for receiving elements from the remote or local mappers. The system is also doing some fancy optimization. So actually when the mapper and the reducer are running on the same machine, they'll just switch this buffer to the reducer without sending it through the network stack. But this will help you to understand roughly how many buffers you'll need. So if you have a simple map-only job, you'll basically need no buffers because there's not much sending going on. But as soon as you have a repartition, for example, a join or a reduce, you'll need to send stuff through your cluster. And the last thing that you can do for tuning your job or pimping your job is I/O. And what we're doing there is allowing users to specify directories for temporary disk space. So in Windows, you can specify a paging file where the system can spill your stuff when your applications don't fit into the memory anymore. In Flink, we do a similar thing, much smarter, by the way, as you've learned from Fabian's talk. So our algorithms are aware how to spill stuff to disk and when. But still, when the memory is not sufficient, the system still needs to have a location where it can write stuff to. And we'll do this in an asynchronous fashion, so all the internal operators can basically write requests into a queue, and each disk has a reader thread and a writer thread, which will handle all the I/O requests which are in the queue. I would recommend to use all the disks that you have locally, which have enough free space and are fast enough. So I would not recommend to mount memory, for example, as a disk, because then you could just use it directly as managed memory in Flink. And I would not recommend to use remote disks which are attached via network or anything. So for example, in Google Compute, you can start instances with locally attached storage, and they have very good performance, in particular when you're using SSDs. And this is the state what we have right now for debugging, but we are working on more stuff to make it easier. So we are working on per job monitoring and metrics, which will allow you to see how much elements are coming into an operator, how many are going out. You can also see how much we are spilling to disk, how much network traffic the job is causing. So this will allow you to understand how heavy your individual operators are. We are also working on dynamic memory management so that that the memory is not statically divided into these areas, but the system can automatically on demand allocate memory or free memory, for example, for buffers and managed memory. And then the number of configuration values goes down and the out-of-box experience is better. And we are working on some advanced debugging features where you can download the result of a single operator that might have failed, for example, locally, so that you can debug it with your code on your local machine. Yeah, and then there's another option for investigating errors. So the best one is reading the documentation, because remember, Paris Hilton. Or you can use the mailing lists and ask questions there. We also recently started to monitor Stack Overflow. So please tag your question with a Flink tag, and we'll get an email notification, at least some of us. We are also idling on IRC. And yeah, read the code, it's open source. And last but not least, some advertisement for Flink Forward. But I think you've seen it already. All right, are there any questions? Was it too long? All right, then thank you.